A pulley is a wheel on an axle or shaft that is designed for basically two things: to support movement and to redirect force via cable, belt, string, or chain. It is one of the so-called simple machines. It is mainly used to multiply a force. Legend has it that Archimedes used it to multiply his force to lift an entire enemy battleship. The most common questions concerning pulleys are basically, what are the acceleration of the masses involved, and what are the tensions on the strings involving? We will examine some cases, starting from simple to what looks like complex. We are interested in looking at different arrangements of masses and pulleys to learn how to set up the problems and how to think about them. All the setups we will do here will concern only constant forces. A few assumptions are to be made here if we are studying the motion of masses under constant forces. 1. The mass of the string is small compared to the masses in question, small enough to be negligible. This should make sense because once the mass of the string is taken into consideration, there will be a continuous transfer of mass from one side to the other. Obviously, changing mass would lead to a change in the amount of force, and would therefore not be a case of constant forces. Later, we will see the case where the forces change over time, but for now, we're interested in studying the motion of a mass under constant forces. So string, negligible. 2. The string does not stretch or contract, like in the case of elastic bands or springs. This is because any deformation will come with an internal restoring force, which is also not constant. 3. The mass of the pulley is also negligible. This is because we are interested in studying the motion of masses as in particle mechanics. Taking the mass of the pulley into consideration will require rigid body mechanics due to its rotation. We will also do that later, but at this moment we're only concerned with particle mechanics. 4. The pulley does not offer friction at the point of rotation. Or in reality, I should say its friction is negligible, but it offers sufficient friction in contact with the string to avoid slipping. So, friction where it touches the string, but not at the point of rotation. This allows the string and pulley system to rotate, making every point on the string move smoothly. Another version of this condition is to think of the pulley as completely unable to rotate, but with no friction where it touches the string. This, again, will allow every point on the string to slide and move smoothly, with the same effect. All these assumptions are the same for all types of arrangements of pulleys and masses, as long as the focus is on the effect of constant forces on masses. Although physics problems are very unique and there is no recipe for solving them, they do have patterns that will help us analyze them. There are two facts that will be key to solve basically any of these problems. 1. Pulleys redirect forces on strings. That is, they transmit the tension force from one end to the other, no matter how the string bends to change direction. That means that we will always be able to equate tensions. And 2, masses are connected by a string, which makes their accelerations be connected in some way. So 2 masses and 1 pulley. There are only 2 cases we can have: equilibrium, that is, equal masses, and not in equilibrium, that is, different masses. One will be heavier than the other. Let's look at the case of equilibrium first. This is trivial. Here, there is no acceleration because the sum of forces is 0. This weight equals that tension, which is this tension too, and that must equal that weight. When it is not in equilibrium, you must write the equations of motion for each object. But even before we look at the equations, you should notice right away a few things. If m1 is greater than m2, then this weight is greater than t, and this t is the same as that t, and that must be greater than this other weight. The exact values of each of these parameters is determined by the equations of motion. We take a look at one body at a time. We look at m1. The sum of forces for that object must be equal to its mass times its acceleration. And we do the same for the other object. This process will give us two equations with two unknowns. This is solvable. Now consider the case where the pulley is suspended by a string, and suppose you need to find the tension on that string, which we will call P. What would you do? Well, you would probably say that the tension P must be equal to the total weight hanging from there. And you would be right, that's true. And in the other case, you would probably say the same. Unfortunately, that's wrong. These are not equivalent cases. One is in equilibrium and the other is not. In the first case, we got the right answer not because we did the correct analysis, but simply because we were lucky. You see, the tension P is acting on the pulley. And although the pulley is massless and does not contribute to the motion of the two masses hanging, it still requires a free body diagram of its own. If the question is about P, you have to see where P is acting. P is acting on the pulley, so you must ask what is happening with the pulley. What are all the forces on the pulley? So, the correct diagram shows that P equals 2T, and it just happens that T equals mg. On the other case, the diagram shows that P equals 2T, but this time T is not the weight of any of the masses. It's not even the average. The value of T will depend on the equations of motion. Now, let's look at the case of 3 masses and 3 pulleys. Again, in equilibrium, this is easy. These two forces must be equal to each other. These two other forces must also be equal to each other. And that means that m1 equals m3. For the mass in the middle, we see that 2t equals m2g, and so m2 equals 2m1 or 2m3. Whatever you want to use, those two masses are the same anyway. Now the case of not in equilibrium will now look a little bit more complicated. You must pick a direction for how things move. It doesn't matter if you're actually right. You choose an arbitrary direction for the acceleration, and the math will tell you if the direction was correct. You see, if you pick the wrong direction of the acceleration for a particular mass, then your answer will come out with a negative acceleration. If you were consistent and didn't make a mistake in the algebra, you should get the right magnitude, but with a negative. And that's okay, because negative only indicates direction. The algebra will let you know the true direction of the acceleration. For example, let's say that for some reason you imagine that m1 and m3 will be pulling harder than m2. So you decided to pick these accelerations. When you look at each of these bodies independently, you can determine each equation of motion. Now here, you may be tempted to say, wait a minute, this is impossible to solve. This problem is a set of 3 equations with 4 unknowns, A1, A2, A3, and T? Hold your horses. The masses are connected by the same string. This means that their motion is connected too. For this particular case, it turns out that the addition of the accelerations of mass 1 and 3 equals twice the acceleration of mass 2. Let's do one more, and let's see if by now you see a pattern. Look at 2 masses and 3 pulleys. We are going to see the case of equilibrium first. So, because this is the same string, all the tensions are the same. Now, we indicate the weight of each of those masses. Now you look at the body diagram. For m1, m1g equals T. For m2, you can consider the pulley as part of the body and you will have this type of diagram. Here you can see that because the object is not accelerating upward or downward, the forces must cancel each other. So whatever is pulling up must be equal to whatever is pulling down. 3t equals m2g. There are 2 bodies in there. So, just in case you need to actually break them down, let's do that here. When you separate them, you will see that each object requires a normal force coming from the other object. Why? Because of Newton's third law. From the diagram of the pulley, you can see that N equals 2t. And since this N is that N, then this is 2t and this is t. so 3t must be m2g. Now, what happens if these masses are not in equilibrium? Well, now you must take into account the acceleration. You must pick some arbitrary direction of motion and then write for each body the sum of forces which will be equal to mass times acceleration. There are three unknowns, t, a1, and a2. But as usual, since the masses are connected, their accelerations are connected as well. For this particular case, a1 equals 3a2. And since you can write one of these accelerations in terms of the other, then you really have two equations and two unknowns, which is solvable. Now that we have an idea on how to think about these problems with pulleys and what the equations should look like, your next step is to actually solve them.